Welcome to G Fun Facts Online. Today we are diving straight into the mind-bending world of sub-wavelength optics and the future of display technology. For decades, the story of displays has been a relentless drive toward making things smaller. From the gigantic, heavy cathode ray tubes that used to take up half of our living rooms in the 20th century, to the incredibly thin organic light-emitting diode, or OLED, screens that now dominate our pockets and living room walls, the goal has always been the same: pack more pixels into a smaller area to create images that our brains cannot distinguish from reality. But right now, the tech industry is attempting a massive pivot. We are moving toward next-generation applications like fully immersive virtual reality, augmented reality, smart glasses, holographic projections, and even displays built directly into contact lenses. However, traditional manufacturing and standard optical rules have crashed headfirst into a fundamental, seemingly impossible barrier: the physical limits of light itself. Let us break down exactly what is happening. Your standard high-end smartphone today boasts a pixel density of somewhere around 400 to 500 pixels per inch. For a device that you hold at arm's length, this is perfectly fine. Your eye cannot easily resolve the individual dots of light at that distance. But what happens when you take that exact same screen and place it mere millimeters from your eye inside a virtual reality headset? Lenses magnify the image to wrap around your field of view, and suddenly, the tiny gaps between the individual pixels become jarringly visible. You feel like you are looking at the digital world through a fine mesh net. This is known as the screen door effect. It completely shatters the illusion of immersion and causes significant visual fatigue over time. To fix this, to achieve a truly flawless near-eye visual experience that perfectly matches the biological visual acuity of the human eye, engineers have run the numbers. They calculate that display densities must exceed 5,000 to 10,000 pixels per inch. At those ultra-high densities, individual pixels must be shrunk to dimensions smaller than a single micrometer. This is where things get incredibly complicated, because you are now pushing the size of a pixel below the actual wavelength of visible light. Visible light ranges from approximately 400 to 700 nanometers. When you try to scale optoelectronic components down into these sub-wavelength realms, the conventional architecture of an OLED simply breaks down. Light begins to diffract unpredictably, materials literally fail and destroy themselves due to intense localized electric fields, and the amount of light you actually get out of the device plummets to near zero. To overcome this seemingly insurmountable barrier, physicists and materials scientists have abandoned traditional optics and turned to the bleeding-edge field of nanophotonics. They are leveraging nanoscale optical antennas and metasurfaces, engineering optical properties at the scale of individual molecules. By utilizing something called plasmonic resonances, researchers are successfully redefining how light is generated, amplified, and directed. They are paving the way for sub-wavelength OLED pixels that are literally smaller than a single bacterium. To truly appreciate the sheer genius of nanoscale optical antennas, we first need to understand why simply shrinking a standard OLED down to a smaller size does not work. A traditional OLED is made up of a stack of ultra-thin organic semiconductor layers. These include a hole injection layer, a hole transport layer, an emissive layer, and an electron transport layer, all sandwiched tightly between two electrodes. When you apply an electrical voltage, electrons and electron holes migrate toward the emissive layer in the middle. They recombine to form a state called an exciton, which eventually decays and releases a photon, a particle of light. In large, macroscopic pixels, these layers form a clean, flat, two-dimensional planar geometry. Everything flows smoothly. But as you aggressively scale pixel sizes down into the nanometer regime, this nice two-dimensional flat landscape evolves into a highly complex, three-dimensional topological mountain range dominated by the sharp contours and jagged edges of nanoscale electrodes. This transition introduces catastrophic failure modes. First, you get spatially imbalanced charge carrier transport. The sharp edges and corners of nanoelectrodes naturally possess much higher electric field concentrations. It is exactly like how lightning rods work. Electricity concentrates at the sharpest points. This causes electrons and holes to be injected unevenly, leading to chaotic and inefficient recombination zones. Second, you get filament growth and rapid device failure. because the electrical current prefers to flow through those high-field sharp edges of the nanostructure. Massive localized current densities occur. This acts like a blowtorch on the microscopic scale. It triggers the growth of conductive filaments straight through the incredibly fragile organic semiconductor layers. This causes catastrophic short circuits and rapid device death, often within milliseconds of turning the display on. And third, you run straight into the diffraction limit. In standard optics, the Abbe diffraction limit dictates that light cannot be easily confined or manipulated in spaces smaller than roughly half of its wavelength. Traditional optical cavities and standard color filters completely fail at these microscopic scales. The result is severe optical crosstalk, where light bleeds uncontrollably into neighboring subpixels, and a catastrophic drop in external quantum efficiency, meaning the device eats electricity but produces almost no visible light. To break through this barrier, light and electricity must be corralled, using entirely different physical mechanisms. Enter nanoscale optical antennas. In our macroscopic world, we use radio and television antennas to convert freely propagating electromagnetic waves into localized electrical currents, and vice versa. The size of an antenna is typically proportional to the wavelength of the radiation it interacts with. For example, a radio antenna might be several meters long to perfectly match radio wavelengths. Nanoscale optical antennas operate on the exact same fundamental principle, but they are scaled down by a factor of 1,000,000 to interact with the extremely short wavelengths of visible light. Fabricated from noble metals like gold and silver, these nanoantennas harness an incredibly fascinating phenomenon known as surface plasmon polaritons. Imagine a stadium full of people doing the wave. When light strikes or is generated near a metallic nanostructure, the electromagnetic field interacts with the free conduction electrons on the surface of the metal. It causes these electrons to oscillate collectively, just like the crowd in the stadium. This collective oscillation creates a hybrid state of light and matter known as a plasmonic resonance. Plasmonic nanoantennas can take freely flowing optical energy and concentrate it into heavily localized hotspots with volumes vastly smaller than the diffraction limit. Furthermore, by carefully engineering the exact geometry, the shape, the size, and the material of the nanoantenna, scientists can precisely tune its resonance to specific colors and wavelengths of light. When an organic light-emitting material is physically coupled with one of these plasmonic nanoantennas, something magical happens. The spontaneous emission rate of the excitons is drastically accelerated. This is a phenomenon governed by the Purcell effect. The antenna essentially reaches in, extracts the energy from the organic layer, and efficiently radiates it outward into the far field. It simultaneously amplifies the light and directs it with laser-like precision. So how has this been proven in the real world? A defining breakthrough in the realization of practical sub-wavelength OLEDs was recently achieved by a team of physicists, led by Jens Pflaum and Bert Hecht at the Julius Maximilians University in Würzburg. They successfully engineered the world's smallest individually addressable light pixel. It measures a microscopic 300 by 300 nanometers. To put that into perspective, the surface area of this pixel is roughly the size of a single biological bacterium, and its overall volume is more than 100 times smaller than standard OLED pixels found in your phone. Despite its virtually invisible footprint, this nanopixel emits orange light with a phenomenal brightness of up to 3,000 candela per square meter. That rivals or even exceeds the luminance of conventional, massive macroscopic displays. The Würzburg team utilized a cuboid gold patch antenna as the bottom anode. This supported the critical plasmonic modes needed to extract light from the sub-wavelength structure. But you are probably wondering, how did they prevent the catastrophic edge effect failures, those short circuits we discussed earlier, that are usually associated with scaling things down this much? Their absolute genius lay in a new concept termed the insulating nanoaperture. Instead of just taking an electrode, shrinking it, and hoping for the best, the team intentionally passivated the sharp edges and corners of the gold nanoelectrode. They deposited a precision-engineered insulating layer using a material called hydrogen silsesquioxane right over those dangerous sharp edges. They covered everything up, but intentionally left a tiny 200 nanometer wide circular aperture completely flat and exposed in the exact center. By forcing the electrical current to bypass the sharp, field-enhancing outer edges and flow exclusively through this smooth, flat, homogeneous central hole, they achieved strictly controlled charge carrier injection. They essentially built a microscopic dam to force the current through a safe, controlled channel. This perfectly stabilized the light emission, entirely suppressed that deadly filament growth, and resulted in a highly robust device. The team demonstrated that even these early prototype nanopixels could operate stably for continuous weeks under ambient conditions, boasting response times fast enough to easily exceed standard high frame rate video rates. While this 300 nanometer pixel represents a massive leap for individually addressable bottom-up OLED architectures, parallel research vectors have approached this sub-wavelength challenge through an entirely different lens: optical metasurfaces. A metasurface is an ultra-thin, artificial planar material constructed from millions of sub-wavelength structures. Think of these as nanoscale pillars, ridges, or corrugations, arranged in a specific, highly calculated mathematical pattern. These tiny structures alter the phase, amplitude, and polarization of light as it reflects or transmits, acting as a flat, nanoscopic lens or optical cavity without the need for thick, curved glass. In a landmark development pursued by researchers at Stanford University and the Samsung Advanced Institute of Technology, these metasurfaces were integrated directly into the OLED architecture. The result was proof-of-concept displays that completely shatter known limits, exceeding 10,000 pixels per inch. To understand why this is revolutionary, you have to look at how conventional high-resolution OLEDs are made. They usually rely on one of two severely flawed methods. The first method is fine metal masks. Red, green, and blue organic materials are evaporated and blasted through a physical metal mesh mask to land on the screen. However, this technology hits a hard manufacturing wall around 600 to 1,000 pixels per inch. If you try to make the holes in the mask any smaller, the incredibly thin metal simply sags under its own weight or breaks entirely. The second method is white OLEDs with color filters. In this setup, white light is generated across the entire back of the screen, and individual subpixels are defined by placing red, green, and blue optical filters over them, much like stained glass windows. While this method allows for much higher pixel densities, the physical filters block and absorb roughly 70% of the generated light. This absolutely ruins energy efficiency, drains your battery, and drastically reduces the maximum brightness of the screen. The Stanford and Samsung Metasurface OLED architecture completely circumvents both of these massive limitations. The researchers took the standard flat metal electrode base and replaced it with a layer of reflective metal, featuring nanoscale corrugations. This is the reflective optical metasurface. When a single layer of white-emitting organic material is deposited uniformly over this metasurface, the nanocorrugations at the bottom act as highly specific optical antennas. By manipulating the resonant properties of light locally, the metasurface physically forces specific colors, either red, green, or blue, to resonate and extract at specific pixel locations. Because the actual pixel color is determined entirely by the physical shape and geometry of the nanopillars buried beneath it, there is absolutely no need for precise fine metal mask deposition, and there is no need for light-absorbing inefficient color filters. All of the organic layers can just be deposited in one uniform blanket across the entire computer chip. The result is an ultra-high-resolution pixel array that boasts much higher color purity and up to double the luminescence efficiency of a standard color-filtered white OLED. Taking this extreme miniaturization even further, research teams from ETH Zurich, the University of Alberta, and other international institutions have utilized single-step nanomaterial engineering to create OLED pixels measuring an absurd 100 nanometers in diameter. By tightly controlling the interaction of these pixels at the very absolute edges of the diffraction limit of visible light, the researchers estimate that maximum pixel density could theoretically be pushed to an astonishing 100,000 pixels per inch. At these scales, the display pixels literally approach the size of human cellular structures. But the story does not end with static pixels. As optical antennas scale down into the deep sub-wavelength regime, they cease to be mere static light emitters. They become dynamic, highly tunable sources of light. This has given rise to the concept of the organic light-emitting antenna, or OLED. In standard commercial displays, a subpixel is fixed, a red pixel is always red, and a blue pixel is always blue forever. But down at the nanoscale, the boundaries of materials science allow for unprecedented versatility. A recent study detailed the creation of an organic light-emitting antenna acting as a color-switchable and directionality-switchable point source. The architecture consists of laterally arranged, electrically contacted gold nanoantennas separated by a microscopic gap. This tiny gap is filled with an organic semiconductor material known as zinc phthalocyanine. This specific material exhibits preferred hole conduction when it is coupled with gold. Because of this unique property, the physical location of the excitant recombination zone, the exact spot where the light is actually born within the nanoscopic gap, shifts depending on the polarity of the applied electrical voltage. If the voltage is positive, the recombination zone couples selectively to the left antenna. If the voltage is switched to negative, it couples to the right antenna. Because these left and right antennas can be physically shaped differently to support different plasmonic modes, shifting the recombination zone dynamically alters the color of the emitted light and the spatial direction in which the light is beamed into the room. This renders traditional transparent electrodes, like the indium tin oxide used in almost all current screens, completely obsolete, as the metallic antenna itself efficiently radiates the light outward. This incredible tunability points to a very near future where a single nanoscale subpixel could function as a full-color, wavelength-scale pixel, capable of physically steering light directionally for advanced glasses-free, 3D, or true holographic display applications. Furthermore, researchers are pushing beyond simple metals. They are exploring high-index dielectric nanoparticles, such as structured phase-change alloys, to achieve multipolar Me resonances. By manipulating active nanophotonic states like the optical anapole, which is a peculiar, low-radiating state formed by the interference of electric and toroidal dipole moments, scientists can actively switch the optical properties of the metasurface with extremely high extinction contrasts. In simpler terms, this allows for the creation of ultra-compact, flat optical surfaces that provide deep, programmable control over how light and matter interact. So where does this all lead? The engineering of sub-wavelength OLED pixels via nanoscale optical antennas is not just some fun academic exercise to write papers about. It represents a foundational, enabling technology for a massive array of next-generation devices that will change our lives. The most immediate commercial impact will absolutely be felt in the extended reality space. With pixel densities easily reaching 10,000 pixels per inch, the screen door effect is mathematically and physically eradicated. Virtual reality headsets will become dramatically lighter and thinner, as the complex, bulky magnification optics currently used can be vastly simplified. The sheer brightness of plasmonically amplified OLEDs, maintaining 3000 candela per square meter or higher, is totally critical for augmented reality smart glasses. These glasses must project digital images bright enough to be clearly visible against the glaring backdrop of natural daylight. Eventually, this precise technology is the absolute key to producing displays small enough and energy efficient enough to be integrated invisibly into standard prescription eyeglasses, or even printed directly onto smart contact lenses. Beyond consumer displays, the ultra-compact, high-intensity nature of nano-OLEDs opens revolutionary doors in biological and scientific imaging. Imagine a dense array of 100 nanometer nanopixels acting as an individually controllable, programmable light source to illuminate the most minute, hidden areas of a biological sample. In tip-enhanced Raman spectroscopy, optical antennas heavily loaded with multiple plasmonic nanoparticles can dramatically amplify the extremely weak Raman scattering signals of single individual molecules. This allows scientists to spectrally map chemical compositions at a jaw-dropping 20 nanometer spatial resolution. Then there is the world of computing. As computer silicon chips rapidly reach the absolute thermal and physical limits of Moore's law, transitioning from electrical copper interconnects to optical light-based data transfer directly on the chip is paramount. Sub-wavelength OLEDs and highly directional nanoantennas can function as ultra-compact laser sources and optical switches. They can transmit massive packets of data across a silicon motherboard with almost zero heat generation and literally at the speed of light. Moreover, dynamic metasurface flat optics driven by these nanoscale emitters can achieve high-speed beam steering, hitting solid-state scanning speeds well above 10 kHz, which proves vital for ultra-compact LiDAR systems used in autonomous self-driving vehicles and next-generation robotics. Finally, we must look at quantum information processing. The marriage of plasmonic patch antennas with quantum dots and other single-photon emitters offers a highly scalable platform for quantum plasmonics. By precisely engineering the exact spontaneous emission rate and the directionality of single isolated photons, these nanostructures will form the core backbone of integrated quantum photonic circuits. These are totally necessary for unhackable quantum communication networks and the holy grail of computing, room temperature quantum computers. Of course, despite all of these breathtaking lab results, transitioning nanoscale optical antennas from a highly controlled cleanroom to global mass production entails substantial manufacturing hurdles. The fabrication of high aspect ratio, three-dimensional multi-material nanostructures with precise dimensional control is notoriously difficult and expensive. Currently, many of the prototypes rely on electron beam lithography, a process that traces intricate patterns with a focused electron beam. While this offers phenomenal precision down to just a few atoms, it is painfully slow and completely unsuited for commercial mass production. However, viable solutions are quickly emerging. The Stanford and Samsung metasurface architecture utilizes a process called nano-imprint lithography. This operates very much like a physical stamp. A perfect master mold of the metasurface corrugations is created once, and then it is physically pressed into a chemical resin over a large area, perfectly replicating the pattern millions of times in seconds. This technique is already highly scalable and is actively used right now in the manufacturing of advanced solar cells, strongly suggesting that high-throughput, cheap production of 10,000 pixel per inch metasurfaces is economically viable. Another major challenge is metallic absorption. While noble metals like gold and silver enable magnificent plasmonic resonances, they also inherently absorb a fraction of the visible light as waste heat. To push the external quantum efficiency of nano-OLEDs well beyond the current 1% benchmarks and toward the 20 to 30% efficiency seen in macroscopic OLEDs, scientists are actively exploring hybrid material systems, all dielectric high-index nanoparticles, which completely minimize absorption losses, and highly engineered three-dimensional nanoprinting techniques. Recent breakthroughs in three-dimensional nanoprinting have allowed for the single-step fabrication of vertically standing, high-aspect ratio hybrid gold and silver nanoantennas with feature sizes below 80 nanometers directly on silicon substrates. This vastly reduces substrate energy losses and perfectly broadens the operational bandwidth across the entire visible light spectrum. In conclusion, the fusion of nanoscale optical antennas with organic light-emitting diodes represents one of the most exciting, paradigm-shifting frontiers in modern applied physics. By completely abandoning the brute force approach of simply shrinking old macroscopic planar designs and instead embracing the highly complex sub-wavelength realm of plasmonics, metasurfaces, and nanoapertures, brilliant scientists have successfully shattered the diffraction limit of pixel density. From the 300 nanometer, individually addressable insulating nanoaperture pixels pioneered at the Julius Maximilians University, to the 10,000 pixel per inch filterless metasurface displays developed by Stanford and Samsung, these brilliant innovations are systematically dismantling the physical barriers to flawless, hyper-realistic digital optics. As advanced manufacturing techniques like nano-imprint lithography mature over the next few years, these sub-wavelength light engines will inevitably move out of the sterile laboratories and into our daily lives. They will permanently alter how we visualize our digital data, how we interact with augmented virtual worlds, and how we peer into the microscopic fabric of reality itself. Thank you for tuning in to G-Fun-Facts Online, where we explore the bleeding edge of science and technology. Keep wondering, keep exploring, and we will see you in the next deep dive into the future.